Hi, I'm Isaac Newton. Would you like to learn how to find the area under a curve? Well, come on aboard the Calculus Mobile and let's go for a ride.
I wish I knew the area of the curve under my Z so I could get to Excelsior with precision.
I know a guy. Newton. Oh, look, it's Newton.
Look, it's Newton, yeah.
Guys, that's simple. Just integrate it so you find the area under the curve.
Integrating? What's that?
Well, I'll show you. This is calculus.
Integration is so intense, I had to invite my buddy, Leonard Euler, here to help me out. Come on in, Euler.
Have no fear, Leonard Euler's here.
That's right, have no fear. So, Euler, what's up?
Well, Newton, I see you have a problem,
That's right.
and I want to help you solve it.
Well, you can.
Okay then. Well, say we have, here's a graph. Say you have a curve like that. How do you find that area?
Oh, that shouldn't be a problem. I know exactly what I'm doing, but for your sake. Well, what would you do? Because I know exactly what to do. Well, your second grade teacher used to divide, like if you wanted to find the area of this little lake or something, you'd partition it into these little squares. Right here. Like that. You see? It wasn't, exactly right, but it was a close approximation. Well, that's the same thing we're going to do here. It's no different. I'm going to partition this into little rectangles this time.
But boy, how can you do that?
Oh, I'll show you. Yeah, check it out. Rectangles right there. Another one right here. Notice the right endpoint of the rectangle is on the curve. Oh, there's another one right here.
But can you use the left endpoint if you wanted to?
Can you use a left endpoint if you wanted to? This is integration. Possibilities are endless.
Oh boy, golly. This is so exciting.
So either way, you're trying to get an approximation for the area under this curve. Well, again, just like the little lake I drew before, there's gonna be some error involved in this approximation. If you look closely, you see all this little gap right here? That's gonna be a big problem. All this over here, that's not actually under the curve, but it's included in the approximation. So what are we gonna do? Any ideas, Euler?
You know, Newton, I did learn something back when I was a little baby, and something called integration.
Integration? Oh.
Well, you want me to tell you what it is?
Show us, good sir.
Okay, instead of using a little box method here, it's something quite easier. Okay? So, there's this symbol we call. See that symbol?
Whoa! That's a pretty nifty symbol, don't you say?
Okay, so let's say this curve is, I don't know, sine curve wave. Okay, so here we go, we wrote a little symbol. It's sine of x. And with integration, there's this nifty thing called with respect to x.
Okay. If you get that wrong, it's a sin.
So, we want to find out where the sine curve intersects the x-axis. And we all know that's at 0 and
Pi.
pi. Yes, pi. So, we put our limits of integration on the integrand from 0 to pi.
Ooh, that's fancy.
Oh, is it? I know it is. Now, I mean, if you have a calculator, you can do it like that. But we don't have calculators. So,
What do you think this is? The 21st century?
So, I'm going to tell you how to find it without a calculator.
Well, while Euler's trying to figure that out, I'll get back to my little square method, rectangle method right here. Notice, there was lots of error involved because my rectangles were pretty big. But what if I made my rectangle small? Could you hurry up? I'm getting there. You impatient 300-year-old man. Anyway, you notice, you see the space that's not included in the actual area under the curve? It got a lot smaller. Notice, the smaller these rectangles get, the better approximation I get. It's directly proportional. So, what if I made my rectangles so small that that it's just so itty tiny that it would approximate the graph perfectly without any error?
Well, Newton, that's exactly what that is.
Whoa! Fantastic!
And boy, you want me to show you how to do that?
Oh, do I ever?
Now, with integration, sometimes called the antiderivative. So we all know that the derivative of negative cosine is sine. So the reverse of that, the integration of sine becomes negative cosine of x.
It's like differentiating, but backwards.
And then, can't forget these two numbers, 0 and pi. So, we evaluate this negative cosine x from pi to 0.
Pi to 0? Well, that's the area we want to find.
So when you do it, you have negative cosine of pi, and then be a minus because you have to subtract the things. Okay, but it's going to be a minus, so that really turns it into a plus, but we'll really worry about that later. To the cosine of 0. Now, Newton, what's the cosine of pi?
The cosine of pi is -1. But wait, there's a negative side in front of that.
So that makes it just a good old 1.
Positive 1.
And,
Are you positive?
and you know the cosine of 0, right?
Yeah, it's 1.
So we have a -1 here, but once again, negative times a negative makes a positive.
Are you positive?
Oh boy,
That
golly am
never
I.
gets old.
And we know that 1 plus 1 equals 2.
Not window.
So, we now know that the area under this curve is 2 units squared.
Why, by golly, we just solved the mystery. How do you like that, Mr. Graph?
Well, kids, I hope you learned a lot today. Sure did, Newton. Now you guys have the information to find the area under any graph in the world. Oh, possibilities are endless. Sorry, kids, but I gotta get going right now. But tune in next week to find the approximations for Taylor and McLaurin series.
I know I'll be there.
I gotta get going. I'm Isaac Newton. Stay safe.
Bye, Newton.